Yeah, comes on everyone. Let's start off. So last thing we have started with refraction on curved surface. Let's go ahead. Let's do a few more problems on this. Let's say mu is 3/2, mu is 2. Radius is 20 centimeters. We have an object here going with 2 centimeters per second. Find the velocity of the image in the ground frame. Let's get this. Remember, you can't use the mirror ka formula which we derived. dv by dt is v minus v squared by u squared du by dt. This is a refraction on curved surface. So you have to derive the formula again. Let's get this. Others, keep your cams on. So how do we even start? Always, whenever they ask you for velocity, go back to the basic formula. What is the formula? Mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r. Differential with respect to time. Minus mu2 by v square dv by dt. Here r is constant, so this term becomes 0. This gives you velocity of image with respect to the pole. Mu1 v square by mu2 u square, velocity of object with respect to the pole. Remember, all these are velocities with respect to the interface. Luckily here interface is not moving, but if it moves, you have to take relative velocity. The formula keeps changing, so you can't use the same formula for everything. That's your velocity of the image with respect to the pole. Mu1 v square by mu2 u square, velocity of object with respect to the pole. Clear with this? Now you just need to find u and v and substitute here. So what is v? Mu2 is 3/2. V minus mu1 is 2 minus 20. Mu2 minus mu1 is half and r is 20. That is minus 1 by 40 minus 4 by 40 minus 5 by 40. So 3/2v minus 1 by 8, and we get v is equal to minus 12 centimeters. It's a virtual image. So velocity of the image with respect to the pole will be mu1 v square by mu2 u square, velocity of object with respect to the pole. Mu1 is 2, 3 by 2, v square is 12 square, u square is 20 square, and this is plus 2. How much is this? 4 by 3, 12, 12, 400, 2, 2, 200, 3, 4, 25. How much is this? 9 by 25 into 2. 24 by 25. Okay. That means this thing, the image is forming somewhere here. It's virtual and it is going in the direction of light rays. So these image light rays are actually going off like this. When you retrace, it's forming a virtual image. Clear with this? There, the main thing is you have to differentiate this formula. All got the idea there? So be careful, you can't use the same formula for everything. Mirrors, lenses, refraction curved surface, it keeps changing. Next one, any doubts on this? We got a mirror here. This refractor index is 3 by 2. Outside is 1. R is 10 centimeters. This is silvered here. R is 20 centimeters. Object is here. This distance is 40 centimeters. This distance is x. Find x if the final image forms on the object. Remember how many phenomena are happening here? Refraction on curved surface, reflection, refraction on curved surface, then image. 3 things: refraction, reflection, refraction. But again, whenever you hear these questions, right, find x if the image forms on the object, these questions actually become easy to solve. Think. Let's see how will you do this thing. I'll give you 2 minutes. Now see, first let's find the image for the refraction that you can do. There are actually two answers for this case. That's what makes this problem special. Most people, right, we don't realize there is a second option. First, do the refraction here for the first surface. Mu2 is 3 by 2. V mu1 is 1 by minus 40. 3 by 2 minus 1 is 1 by 2, 10. That's 1 by 20 minus 1 by 40, 1 by 40, 60 centimeters. That means these light rays are forming an image here at 60. Now there are two possibilities here. The first possibility we already know, the image should form at the center of the mirror. If this image I forms at the center of the mirror, light rays will retrace the path. So this is the image. Light rays will go like this. Will retrace and retrace. This is also the center. So this distance will be 20 centimeter. This is 60 centimeter. X is 80 centimeter. This is fine. Now what most people don't realize, there's one more case, right, Niharika? Nee, Aditya. Right, Ahana. The second case is the light rays go in, the image forms at the pole. Pole is special. Image I forms at the pole. See what happens. So when you take the object here, the light rays which hit the pole, remember what will happen? They will retrace like this, isn't it? Because this angle and this angle will be equal. So the same light ray doesn't come. So the light ray which goes up will come down, and the light ray which goes down, that will go up. Is that making sense? So the image gets inverted, but the image forms at the same place. Clear? So it's not retracing the path, but they're doing something like that. So this is the case when you're 60 centimeters. So these are the two possibilities. If it's a more than one choice question, mark both of them. So keep this in mind. You can form the image at the pole of a mirror or image at the center of the mirror. Both are acceptable. These are pretty, this is this model, right? The image falls on the object itself. We have already seen once before. This is the second time. You'll see again in lenses. So whenever you get these kind of questions, no one is expecting you that you will solve refraction, then you will solve reflection, then you will solve. There's no need to do all that. You just need to realize after refraction, the image should be at the center of the mirror or at the pole of the mirror, and you're done. That's it. There's no need to solve further. Clear with this? So that's a bit about refraction on curved surface. As such, there's not really too much on this, but quite an important formula. The next thing is thin lenses. So thin lenses is nothing but a special case of refraction on curved surface. So what is a thin lens? So a lens is a transparent material. Lens is made of a transparent material. With at least one curved surface. This is your principal axis. Here we don't call it as pole, we call it as optical center. The center of the lens is called as optical center. This thing, if you look at from the left hand side, you see convex. If you see from the right hand side, it is also convex. So this is called biconvex. This thing is from both the sides concave, so it's called biconcave. This is left side is a convex, right side is a plane, so it's called convexo plano. This is called plano concavo. This thing is left hand side is a convex and the right hand side is a concave. So convexo concavo. So depending on from which side you're saying, you can call it whatever you want. It really doesn't matter for the problem part. Now, in lenses, we study only for thin lenses. So how do you define what is a thin lens? So when you say thin lens, the thickness of the lens must be very, very small compared to the radius. T must be much, much less than R1 and R2. Example, let's say R1, R2 is 20 centimeter. We are expecting thickness to be around 2 millimeters. It's very small. The smaller, the better. So the kind of formulas we get for lenses are only valid for thin lenses. If the lens is thick, then you have to go back to refraction on curved surface. Isn't this kind of looking like a thick lens? Or even this problem? So if you have thickness for a surface, refraction on curved surface is a more powerful formula. So the lens is actually a special case of refraction on curved surface. We'll see that. Everyone clear with this page? Then we define focus again. Now you can define focus for a system also. So if someone gives you a mirror, lens, and everything, and they ask you what is a focus, this is how we define. When parallel paraxial rays are incident on a system, the point where they meet or appear to meet is called the focus. So if you take a biconvex, so if you send a parallel beam here, this thing generally converges light rays. So in HSC book now, it is written as converging lens is a biconvex lens, which is actually not right. We will see later on. These light rays will go like this. So they don't converge here, but when you extend them, it feels like they're coming from here. That's the focus. Now in lenses, we have 4 special light rays, just like in mirrors. If you send a light ray through the focus, it becomes parallel. If you send a parallel light ray, it passes through the focus. If you send a light ray through the optical center, it goes undeviated. If you send a light ray through 2F, it passes through 2F on the other side. The 2F behaves like center, but there's no concept called center in lenses. So these are the 4 light rays. So whenever you want to trace an image, take any 2 of these light rays. The point where they meet is the image. Remember, we did the same thing in mirrors. You used to take two light rays from the object. Generally, you take any of these two light rays, and after refraction, see the point where they meet, and that would be the image. So we will see the tracing of images here also, just like we did in mirrors. It's quite important, especially for theoretical questions. Clear with this? We got a bit of a theory. So the same thing which we did in mirrors. So object is at infinity. The image will form at the focus, real, inverted, highly diminished. Have a look at this. Image is beyond 2f. Object will form between f and 2f. It is real, inverted, and diminished. The results would kind of look like concave mirror ka results. Have a look at the page once. Let's see next one. So if you keep the object at 2f, you get the image at 2f. Like I said, there is no center of, there's no concept of center for lenses, but this 2f behaves like that. So kind of it's decent to remember. And not only this, we will prove this later on. The minimum distance between the real object and real image is 4f. The object and image can't get closer than this. If you try to push the object here, the image will go even faster, far away. So the distance will always keep increasing. So 4f is the minimum distance between object and the image. Here, image is forming between f and 2f. So here the image forms beyond 2f, which is a real, inverted, and magnified. Clear, everyone? You should definitely remember these cases and for the mirror cases, because whenever you get theoretical questions, I'll ask you one. You will need this stuff. This is the case. When object is at infinity, object is at focus, image is at infinity. Object is between f and the optical center, image is virtual. It's a virtual image, erect and magnified. Clear with the 6 cases? Can you see the results? They look kind of like concave mirror. The only difference, concave mirror images used to form here and just getting reversed. Let's say a question. Same thing. We did this in mirrors. I will do it again. So if you got a lens, so if an object is going this way, draw the path of the image. And if I keep a box here, draw the image of the box. Let's say this is f and this is 2f. Two questions. There, I didn't give any formulas of focal lengths, nothing. Theoretical questions would be of this sort. So if you don't know those position of the images and all, you will have a difficulty getting these kind of questions. Get them. I'll give 2 minutes. Same thing we did in mirrors. Let's see. So first worried about this. How to do these kind of questions? So if you remember, take some arrows. Take an arrow at infinity. This is 2f and f. Take an arrow here. Take an arrow here. Take an arrow here. Take an arrow here. Take an arrow here, and take an arrow close to here. So we have arrow 1, 2, 3, 4, 5, 6, 7. So draw the images for the 7 arrows and then join the head of the arrows. Isn't that the path? So on the other side also we'll have f. We also have 2f. So arrow 1 will be here. Arrow 2 will be somewhere here. Arrow 3 will be here. Arrow 4 will be here. Arrow 5 will be at infinity. So if you join them, this is how it will look. If you remember, it was the same answer, but concave mirror it used to come on the left hand side. Left becomes right, right becomes left. And once you cross 5, the image becomes virtual. So if you're 5 minus, image is at plus infinity, 5 plus, the image will be somewhere here. So there's one more arrow here, 5. So 5 will create 2 arrows, one on the virtual, if it is little more, and then 6 will be somewhere here. 7 will be here only. This is how it looks. Agreed? And if you take a box here, you can clearly see here the box would look between 4 and 5. This will be the image of the box, isn't it? It won't even be a trapezium or quadrilateral, meaning, yeah, it looks curved and all that stuff. It looks like this. The box will look like this. Making sense? Meaning if I try to join that on 4 now, so then it will look like this. Yeah, that's how the box would look. Decent question. Nothing to solve and all. If you know your images, this thing is easy to solve. But yeah. Any doubts on this? Same thing, we did in mirrors. So the idea was the same. Next thing. Same thing if I do for biconcave. Luckily, biconcave, we have only two things. The image is always virtual, just like convex mirror. If the object is infinity, the image will form at the focus. If you place the object here, you can send one light ray through the optical center. It will go undeviated. You can send one light ray parallel. This will try to pass through the focus. So the image will form here. So there are only two cases for a biconcave: object at infinity, image at f, virtual, erect, highly diminished. Here image is erect. Virtual, diminished. Clear with this? Convex mirror ka results. So biconcave will always create a virtual. And same thing, we draw the graphs, remember? So we also have graphs here, same thing. This is the graphs for U and V in case of lenses. This is your X and Y axis. If you actually carefully observe this thing looks like, you know, concave mirror का graph, उसमें graph ऐसा होता था, याद है? Concave mirror में same graph, it is reverse of that. So do check out these graphs later on. You should definitely know these graphs. Now, it's always easy to draw them, but like I said, it is always easy to eliminate the graphs. Drawing is actually a pain. You know, if the object is at 2f, image is at 2f. Object is at pole, image is at pole. Object is at f, image is at infinity. So if you know these few points, you can see which graph doesn't work and you can eliminate them. This will be hyperbolic functions. Clear with this? So that is about tracing of images and all, but now let's try to get the formula. Now here the derivation is important. So for the previous things, you have not done the derivation. The derivation is not that important, but the Lenska derivation is important because there are few ways you can goof it up. Then you need to get back to the derivation. So listen carefully for this. We call this thing Lensmaker formula. So if you have a lens, mu L, outside is mu M. Now this lens could be concave, convex, anything. So R1, R2 can be positive or negative. We'll just keep them as it is. Now, if you have an object here, if you actually think about this, a lens is nothing but refraction on curved surface 2 times. This will be your first refraction. So when the light rays hit here, they will actually try to meet somewhere here. So this I1 will be the object for the second refraction. So it's actually a virtual object. This is your second refraction. So then this light rays, instead of going and meeting at I1, they would meet somewhere here. So we have to use refraction on curved surface 2 times. So when you apply the formula for the first refraction, again, like I said, we will take R1, R2 as it is. The signs will later on will take care. Mu lens by V dash, let's call it V1, minus mu medium by U is equal to mu lens minus mu medium by R1. So U, R1, R2, all will be taken as signs. So here, when you got V1, now this is the catch here, see. All distances are measured from the pole of this thing. So there are 2 poles for the lens, P1 and P2. So here, the distance which you got, V1, is nothing but P1, I1. Now, when you apply for the second refraction, this is the problem that we are facing. The image is forming I1, but the distances are supposed to be measured from P2, isn't it? If this distance is T, and if this distance is V1, so this distance will be V1 minus T. Making sense? You have to measure for the second refraction, the distance are measured from P2. And this I1 is actually a virtual object. Do you guys remember what's a virtual object? The meaning of virtual object is, let's say the light rays were supposed to go and meet somewhere here. I'll give you a scenario here. Let's say we have a lens. The light rays are supposed to go and meet somewhere here, but you went and kept something in the middle. Maybe you kept a mirror. So these light rays were supposed to meet here. So that was a virtual object, but you kept a mirror in the middle. They will reflect and form an image somewhere else. So this point I1, the point where the light rays are supposed to meet, will act like an object for the whatever system it is there. Technically speaking, there are no light rays there. That's why it is virtual. It behaves like an object. So here I1 is a virtual object for the second refraction. So when you apply the formula, again, refraction on curved surface for the second part, mu m by V2 minus mu lens by distance will be measured from P2, so V1 minus T. The object distance will be P2 I1 is equal to mu M minus mu L by R2. Now, if the lens is thin, this is where you get an advantage. If lens is thin, T will tend to 0. Then V minus T becomes equal to V1. Your equation becomes mu M by V2 mu L by V1 mu M minus mu L by R2. This will be your equation 2 and this will be your equation 1. Add equation 1 plus 2. When you do that, you will notice this term here and this term here will cancel out. That is the advantage of a thin lens. If the lens is not thin, those terms won't get cancelled. And you end up with mu M by 1 by V2 by 1 by U is equal to mu L minus mu M 1 by R1, 1 by R2. Is everyone clear what we did? We just used the refraction on curved surface twice. That is one. Second thing, the distances are always measured from the respective poles. For the first refraction, all distances are measured from P1, all distances are measured from P2 for the second refraction. If the lens is thin, then P1, P2 becomes 0, then your life actually becomes easy. Then when you combine all this, you end up with a formula 1 by V minus 1 by U is equal to mu lens by mu medium minus 1. The result is important, but yeah, derivation is also important. I'll show you later on how they will mess it up. This is your formula there. So you can note down this thing. So the final formula is 1 by V minus 1 by U is 1 by F. It looks like mirror ka formula with a minus n in the middle. But your focal length is not that easy. Mirror में it was R by 2. Here it is mu L by mu M minus 1 into 1 by R1 minus 1 by R2. And the magnification is V by U. There, note down these formulas. You will need this. Like I keep saying, the formulas are different, but every technique that you did in mirrors and refraction on curved surface, everything is valid. These formulas are valid only for thin lens. If the lens is thick, then just use refraction on curved surface, forget about lenses. Second, medium must be same on both the sides. Why is that? Go back to the derivation. If the medium on both the sides is not same, then here this will be mu m dash. This will be mu m dash. Then when you add them, the mu m won't come out common. This mu m won't come out common. The whole formula gets messed up. You getting the problem? That is the question we'll see later on. What if the medium is different on both the sides? That is a pretty good question. Means I'll give you a lens where mu1, mu2, mu3. You'll have 3 mediums. That's a pretty good advanced question. So you have to go back to the derivation again then. And as usual, U, V, and R must be taken with sign. Yeah, they do follow sign convention. In the derivation, I took the example as a biconvex lens. Now, I could have taken example as this also. I could have taken this also. I could have taken any lens. So I'll just R1, R2 as it is. So depending on the lens, R1 and R2 will have respective signs. All clear with the formulas?
Sir.
Vihan.
Sir, could you scroll back to the derivation? Yes, sir. So in the second refraction, why is like I didn't understand why mu m is on V2 and mu L is on V1 minus T. Like,
Array, light rays are going outside, right? What is mu1 and mu2? Mu1 is the incident medium. For the second refraction, where are the light rays coming from? mu L.
Hmm.
Where are the light
Okay.
rays going? Mu M. So mu M is
Hmm.
mu 2 and mu 1 is mu L.
And so the image is virtual, so it's like on the other side,
So
but not
the
in the
light rays were
medium.
no. Light rays were supposed to, it doesn't matter, right? Chalo, let them meet here only, na. But where are the incident light rays? There is
Hmm.
nothing called object and image. Incident rays, refracted rays. Where are the incident rays coming from? For the second
Like,
refraction, where are the incident rays coming from? Mu L. Let the image form anywhere, I don't care.
okay, so we'll measure it as a virtual image from the pole.
It doesn't matter. This is what you're thinking. You're thinking, what if the light rays meet here, aisa, andar? Like this? No. Just think of like this is the first refraction. When they hit
Hmm.
here, but this surface, if you ask where are the incident rays, what it will think? These are the incident rays.
Hmm.
In which medium are there? They are in mu L.
Lens.
After refraction, they came out. Which medium they went into? Mu M.
Yeah.
That's mu 2. That's it.
What is
Got it? That is how you keep it. Don't remember as mu 2 is the medium where the image forms. Mu 1 is the medium where the object is. Don't think like that's nonsense. You'll get confused. If you look at here, the virtual object is actually outside.
Hmm.
Don't remember like that. Remember it as a medium of incident rays, medium of refracted rays.
Yes, sir.
Always.
Got
If
it.
you remember the sign convention also, direction of the incident rays is positive. It is always the incident rays are the main ones, not the object and image.
Yes, sir. Got it.
Now, there is one more thing here about theoretical. They'll ask a question like this. Is a biconvex lens a converging lens? If you take a biconvex lens, is this a converging lens? The answer is no. Because if you actually look at the focal length formula, mu L by mu M minus 1, this was something like this was asked, I think, in more than one choice or something as a statement question. Everyone just blindly wrote converging lens and game because in HSC book it is written that way. The problem here it is, if you observe, if mu lens is greater than mu medium, the focal length is greater than 0. That means if you send parallel light rays, they will meet at a focus which is in the ahead. This is a converging lens. But if mu L becomes less than mu medium, if the medium outside is more denser, then your focal length becomes negative. Means the light rays will actually try to meet behind. That means it's becoming virtual image. This is a diverging lens. So there is no guarantee a biconvex lens is always converging. It depends on the mediums. So just keep that in mind. Similarly, if you take a biconcave lens, if mu lens is greater than mu medium, here the focal length is negative. If mu lens is less than mu medium, here focal length is positive. In this scenario, this will diverge. In this case, it actually converges. There. So in the options, they'll make it like this. Mu L greater than mu M, mu L less than mu M. They'll give 4 cases. And they'll ask you, biconvex is converging, diverging. If you blindly remember biconvex is always converging, you'll get trapped. Clear with this? There, that's a bit about a theory about the lenses and the tracing of images and the formulas. Let's see if you have questions on this. Let's see 1 or 2 questions so that you get used to the formula. Find the image. Find the focal length and the position of the image. Hope everyone copied these formulas. Just get this. There's nothing there, just substitution. All the concepts you did in mirrors, image formation, if the object is above the principal axis, drop a perpendicular, all that story is same. (160 centimeters). I'm not sure though. Let's see the focal length ka formula first. 1 by f is mu lens by mu medium minus 1. 1 by r1 by 1 by r2. Mu lens is 3 by 2. Mu medium is 4 by 3. What about r1, r2? Look at this. Lighters are going to the right, so this is positive. So for r1, the center is on the right hand side, so r1 is positive. R2 ka center is on the left hand side, so R2 is negative. Are you clear? That is one thing, but generally you can actually kind of remember this. This R1 and R2 will be such that both the terms will always add up, meaning R1 will be always positive, R2 will be always negative for biconvex. That is the way we have taken the sign convention. If you use coordinate system now, that will keep getting messed up. But in our sign convention, R1 will be always positive, R2 will be always negative for biconvex. So 1 by R1 will be plus 10, 1 by R2 will be minus 20. How much is this? 9 by 8 minus 1, 1 by 8, 3 by 20, 160 by 3. Looks like numbers are bad. Magnification is what? V by U. That's also formula I gave you, didn't write? Magnification is V by U. Minus n won't be there. And then apply the formula 1 by V minus 1 by U is 1 by F. 1 by V, U is negative minus 20. Focal length is 3 by 160. It goes that side, it will be 3 by 160 minus 1 by 20, multiply 8 and 8. That will be minus 5 by 160. We'll get V is minus 32 centimeters. Yeah, this is forming a virtual image. Because I kept this thing between focal length is 160 by 3. I kept it between focus and pole. Yeah, and what about the magnification? Magnification is plus V by U. Minus 32 by minus 20. This is a 4 8s are 4 5s are 8 by 5. There. So your image will be at 32 centimeters and this will be 16.5 by centimeter. This is the image. 16 by 5 centimeters and 32 centimeters behind. This is forming virtual. All got this? Check it out. Sign convention, formulas, everything. Any doubts on this? Anything, any sign convention you're clear? Let's see one more like this. Find the position of the image. Get this again, just a formula substitution. Hmm. Let's say I don't know the answers. Just made up the numbers. Focal length is -10. 1 by f, mu length is 3 by 2, mu medium is 1, 3 by 2 minus 1. Here also again same logic. R1 will be always negative, R2 will be always positive. R1 ka center is left hand side, R2 ka center is on the side, that side. This is 1 by -10 minus 1 by +20. Check the signs. C1 ka center is left side and C2 ka center is right side. So C1 is R1 is negative and R2 is positive. This will be half and that would be -3 by 20. Focal length is -40 by 3. Then apply the image ka formula 1 by V minus 1 by U, which is -40 minus 3 by 40. It goes that side. It becomes, yeah, V is -10. Magnification is V by U, which is -10 by -40, 1 by 4. So the image is 3 by 4 centimeter. 10 centimeters behind. It's virtual. Yeah, it looks like most of you got it. All got this? Easy stuff, direct substitution. There's nothing much to think. Let's see one more. We got a slab, mu is equal to 2. We got a lens. Then this is 20 centimeters. This is -10 centimeters. Outside is 1. This is the object here. This is 31 centimeters. This is 20 centimeters. Find the final image. Slab, lens 1, lens 2. Hope you remember slab ka formula. T into 1 minus 1 by mu. Here I already gave you the focal length, so there's no need to calculate. Minus 40 by 3. U of lens to be taken as what? What are you talking? What is U of lens matlab? Refractive index.
Yes, sir.
I already gave you the focal length. Why you need it?
Okay, yeah. Got it.
There I gave na 20 minus 10. Biconvex is positive plus 20. I gave biconcave minus 10. I already wrote with the sign. So in case of don't give the sign, still you have to take minus 10 for biconcave. Let's see. This was not tough. So what is the shift here? The apparent shift is t into 1 minus 1 by mu. This comes out to be 1 centimeter. So if you ask the lens boss, where is the object? It will say 30 centimeters, not 31. So if this was the object, the image gets shifted here, O dash. This is 1 centimeter. This is 30 centimeters. This focal length is 20 centimeters. If you apply the lens formula, 1 by V minus 1 by U and 1 by F is already given. So you don't need focal length. How much is this? V will be 60 centimeters. Meaning these light rays from here are trying to meet at 60 centimeters. But the problem is there is a lens sitting at a distance of 20 centimeters. This is a virtual object. This is what I was saying. The light rays were supposed to meet at 60, but this guy is coming and blocking in the middle. So the lens will think light rays are coming from O dash. And they're trying to go here and meet somewhere here. Let's call it I1. That is 60 centimeters. So this will be 40 centimeters and this will be 20 centimeters. Is this making sense? So this I1 is actually a virtual object for the biconcave lens. Are you getting the meaning of this? That is the meaning of a virtual object. They're supposed to meet at I1, but you came and blocked in the middle. So the biconcave lens will think, okay, I1 is my object. So here the object distance will be plus 40 centimeters. Use the lens formula 1 by V minus 1 by U, and here F is negative minus 10. How much is this? 1 by minus 1 by 10 plus 1 by 40. 4. So that will be 40 by 3 centimeters. You got a pretty, this is a pretty interesting answer. Huh? You got again a virtual image. So you know what happened? This lens deviated this light rays so much. This light ray which came here, which went away like this. And when you trace them back, you got an image here, I2, which is also a virtual image. So you got a virtual object and a virtual image. So sometimes I can ask a question like this: can a virtual object create a virtual image? It's possible. Is this making sense? The lens deviated the light ray so much, instead of converging, they again went out diverging. So if a person is standing here, if you ask him, boss, where is the object? He will say the object is final here, I2. He will think light rays are coming from I2. He does not know who is O. He does not know who is the slab. He does not know who is this lens. He does not know any of them. He will think this O is here. That's what this person will think. Is this making sense? Most people get confused, when light rays go ahead of the lens, they don't understand what to do. And I'll tell you what is the logic for this thing. See, remember principle of reversibility. Basically, it's think of like this. If you have a lens, if you keep the object here, and if you get an image here, Vice versa. If I keep the object here, I will get the image here. Principle of reversibility. So something of that sort. So whenever you're getting a virtual object, right, and whatever image that you get, if you replace object and image, you'll get the same answer. So yeah, kind of it works. But clear with the concept of virtual object? If the light rays go ahead of the lens or ahead of the mirror, it's a virtual object. They're supposed to meet there, but you're not letting them meet. It becomes positive, and then you solve as usual. And I think now you understand in these graphs why u was positive. U positive are these cases. देखो, in a concave mirror, object is always on the left hand side, na? But that's a real object. Then what is U positive? U positive are the virtual object cases. The light rays are going and meeting ahead, and this concave mirror blocked them. Are you getting it? Take a break. Come back by 9:41. Any doubt so far? Chalo, come back in 5 minutes then. Phi index is the final images on the object. Other scams on. You know the story here. After the lens, the image should form at the center of the pole. Hundred by 3. Here, you'll get two answers na again. Right, Poroja? No, they were wrong. Saish, there's only one answer, right? Maybe one. Maybe one, that is wrong. What is the focal length? 1 by f, 2 by 3 by 2 minus 1, 1 by 20 by 1 by minus 20, that is 4 by 3, 1 by 3, 30 centimeters. One by v by 1 by minus 40 is 1 by 30. 1 by 30 and is 1 by 40, 10, 120 centimeters. That means this lens will form an image at 120 centimeters. So we have two cases. Case 1, this should be the center. This is 120 and this is 20. Radius of curvature is 20 centimeters. So x is 140 centimeters. Or the right is meet at the pole. Got this? You guys must have goofed up the focal length or something. Check your signs. All you need to do is mess up one sign and the whole thing will go for a toss. R1, R2, mu1, mu2, u ka value. You have to be careful. All clear with this? Easy one, but yeah, be careful with the signs. Next thing. Any doubts on this? Yeah, this is the third time you're already seeing the final images on the object. Quite an important model. We got a lens which is moving with 1 centimeter per second. We got an object going with 2 centimeter per second. There, object is moving. And it is not on the principal axis. It is above the principal axis. Lens is also moving. I messed up everything. Lens is moving, object is moving on the principal axis. Find the velocity of the image in the ground frame. Again, remember, you can't use your mirror ka formula. You have to derive for the lens separately. Get this, you got 3-4 minutes. What is the formula? 1 by v minus 1 by u is 1 by f. This is velocity of the image with respect to the lens. Will be v square by u square, velocity of object with respect to the lens. Kind of looks like mirror formula with a minus sign missing. Most important thing, remember, this is not the full velocity. This only gives you the component along the principal axis. So there is also vy component there. So if the object is going above the principal axis, you'll have vx and vy. There will be two components. That's only part of the answer, Rishana. Purvaja, me Aditya, that is wrong. Same thing, Purvaja. You got only the x component. Vy you didn't get. Try. I'll give another minute or so. This gives you only the vx. So let's find 1 by v minus 1 by u is 1 by f. This will be 60 centimeters. Then velocity of the image with respect to the lens, v square by u square, velocity of object with respect to the lens. So you have to stop the lens. This will be 60 square by 30 square, and this will be plus 3. Be careful. That comes out to be 12. Okay. You want velocity of the image with respect to the ground frame, which is velocity of the image with respect to the lens plus velocity of the lens with respect to the ground. Lens is going back, image is going forward. So this is 12y minus I. This will give you 11 I cap. Check. This is not the full answer. This gives you only the horizontal component. Then, no. How do we do that part? We use magnification formula. Magnification is V by U, which is nothing but height of the image by height of the object. So vertical component Vy is nothing but dHi by dt, which is h naught. And when you differentiate this, you get 1 by U dV by dt minus V by U square du by dt. Be careful, dV by dt is nothing but velocity of the image with respect to the lens. Du by dt is velocity of the object with respect to the lens. They're not in the ground frame. Substitute the value. Height of the object is 2 centimeters. U is minus 30. dV by dt is plus 12. This is 60. 30 square. This is plus 3. 15 minus 4 by 5. 32. 6 minus 1 by 5. Minus j cap. There, the velocity of the image with respect to the ground frame will be 11 I cap minus j cap. That's your answer. This gives you the j component. Check the calculations area. Got the steps? I use the product rule instead of division rule. V by U का differential. And when you got dV by dt, du by dt, they are not in the ground frame. dV by dt is still velocity of the image in the lens only. So this is still 12. You can't write there 11. Maybe you did that. You took that as 11. Clear with this? Any doubts on this? There, this is how you do if everything is moving. Lens is moving, object is above the principal axis. Shouldn't we multiply 2 with minus 1 by 5? Didn't I do that? Just send 2 inside. 263, 30, 30, 32 is a 310. I had to do that. I didn't do 2 by 5. कितना था? Minus 6 by 5. I did think it came good. I was happy for a moment. We had just messed it up. ठीक है. It's a wrong answer though. Clear with this? Next thing. We got a lens. We have an object at rest here. 30 centimeters. Lens is also at rest. But this time, this lens ka medium is changing, which is 1 plus t. T is time. So observer is standing here. So if you ask this guy, object is not moving, but the lens ka medium is changing. So focal length is getting messed up. Find velocity of the image as at time 1 second. There, if you mug up the formula of that image ka thing, now you will go off. You will not understand how to handle this. That's the reason you need to know your derivations. Now what will you do? Try. Find the velocity of the image at t is equal to 1 second. Right, Purvaja. What is the sign? Plus or minus? Right, Niharika. Right. Just go back to the derivation. So now 1 by v minus 1 by u is 1 by f, same story. Differentiate with respect to time. But this time, let's find the focal length beforehand. So we know 1 by f is mu length by mu medium minus 1 by r1 by 1 by r2. Here, this is mu minus 1, so that will be t, and this will be 1 by 10. There, actually, your 1 by focal length is t by 10. This actually makes your life easy. So this will be 1 by v minus 1 by u. U is fixed. Is t by 10. Now differentiate with respect to time. Minus 1 by v square dv by dt. I could have moved the object also. 1 by u square du by dt. This is 1 by 10. So here focal length is changing. So du by dt will be 0 now. You're getting it? So that formula is not valid anymore. That formula you derived when focal length was constant. So yeah, and at t is equal to 1 second, your focal length f is 10. So apply the formula 1 by v minus 1 by u is 1 by 10. This is 15 centimeters. This actually makes your question quite easy actually. So dv by dt is minus v square by 10 minus 22.5 centimeter per second. Easy? There, so be careful with that. Every time something changes, just get the formula, differentiate. Can we just use the formula? We get in and do it, no? Nothing wrong. Who said you can't do it? You'll just go mad differentiating such a big function. I also don't like it. This thing, why do you think I gave numbers decently? You can do it, nothing wrong. Just because you multiplied the function, why will the answer change, right? Next thing. Let's say we got a lens. This is y0. This is y 1 centimeter. This is y is minus 1 centimeter. This lens ka refractive index is 2 plus y square. Look at this. This lens ka refractive index is changing with height. So different parts of the lens have different refractive index. Now you took an object here and kept it at 30 centimeters here. Something interesting happens. Find the length of the image. I can ask, like, find the position of the images. So think for a moment what's happening, and then we will see. Take it as one outside. If I don't give anything, take it as one. R also have to give, na? Take R as 10 centimeters each. Take 20 centimeters. What is the catch here? Do you guys remember I taught you something in mirrors? Instead of a full mirror, if you take a part of a mirror, what will happen to the image? Where will it form? It still forms at the same place, but with decreased brightness. So same way, instead of a full lens, if I take a part of a lens, the image will still form at the same place. So for example, if I take a lens, and let's say this thing has two mediums. Let's say the upper lens is made of mu1 and the lower lens is made of mu2. What do you think will happen? The light rays which are going up, they will converge somewhere here. So they'll create one image. The light rays which are going bottom, they will converge somewhere here. They will create the second image. So if a lens is made of two different mediums, you'll get two images. If a lens is made of 10 different mediums, you'll get 10 images. Here, your lens is made of infinite mediums, isn't it? So you'll get infinite images. So all those images will form a line, isn't it? So that one small dot will look like a line. So how do we handle this? Simple, right? At y0, you got mu is equal to 2. Find the image of this. Y is equal to 1, mu is equal to 3. Find these images. So can I say all the images will lie between them? Take the extreme refractive indexes, treat them as two different lenses and find the images. Everyone else must be between them. Is that logic making sense? That's it. So it is simply you have to find the image for two lenses of mu2 and mu3. So that is the main idea there. So if you have a part of a lens, it will still create image as a full lens, but decreased intensity. A part of a lens creates image at the same place. As full lens with decreased intensity. So in our problem, this lens has infinite medium, so you can just finish off with that. 9 centimeters, 90 by 20. I don't think you'll get good numbers. So I can just construct two lenses here. That is 20 centimeters, 20 centimeters. So y is equal to 0, mu is equal to 2. So 1 by focal length will be 2 minus 1. That is 1, 1 by 20, 1 by 20, 1 by 10. Object is at 30 centimeters. So 1 by V minus 1 by minus 30 is 1 by 10. How much is this? 1 by 10 minus 1 by 30, 3 minus 15 centimeters. So the center wala thing will form at 15 centimeters. When y is equal to 1, mu is equal to 3. 1 by focal length will be 3 minus 1, 1 by 10, 1 by 5 centimeters. 1 by v by 1 minus 1 by 30 is 1 by 5. How much is this? 6 minus 1. Yeah, 9 centimeters. You got a good number. That means the lighters which are pretty close to the center, they're meeting here. The lighters at the extreme, they're meeting here. And we can say everyone else will be in the middle. So this will be the image. And the difference will be 15 minus 1, 6 centimeters, right? Am I right? 6 by 30. No, this is 6 centimeters. This will be 9 centimeters. Got this? Easy question once you know what you're doing. But the main thing is that if you make the lens out of 3 different mediums, then you'll have 3 different images and so on. All clear with this? Next one. There, if you see here, I'm messing up with your focal length and all. Mirrors, you couldn't do that. Lenses, you can do all this stuff. This is another decent question. We have 2 lenses, f2 and f1. So you made a setup in order to, make light beams ka intensity, meaning you can converge or diverge the intensities of a light beam. So let's say you sent a parallel beam here. These are normally used in lighthouses. You can take a light beam, compress it and make it more intense. I is the intensity. Intensity is nothing but power by area. And what do we notice when you send a parallel beam onto this, something happened and you also got a parallel beam outside. You sent a parallel beam, you got a parallel beam. And the intensity became I dash. And the distance between the lenses is d. So a parallel beam is incident. And lens 1, and we get a parallel beam from lens 2. This happens for a particular setup. Find d, distance between the lens, and I dash. So by adjusting the focal length, I can change the intensity of the beam. So you can actually diverge a beam or compress a beam. Yeah, distance is easy. Get the intensity. That's the main question. Right, Aditya. Like I said, distance is easy. Get the intensity. That is what I'm more keen on. That is right behind distance. Did everyone figure out the distance? If you send a parallel beam, where will they meet? At focus. If you are getting a parallel beam, where should the image be? At the focus. That means that point must be the focus of both of them. So these light rays they must have gone like this. This is the common focus. I can say it is a focus for both of them. That means this distance is f1. This distance is f2, and you're done. There, d is f1 plus f2. Let me add one statement here. Assume there's no power loss. So what about the intensity? There, Aditya, you are close by. Look at this. If this angle is theta, this is theta symmetry, this is theta, this is theta. If you take this radius as r1, this radius is r2. So this is the radius of aperture, if you remember. And we can see from here geometry tan theta is r1 by f1 is equal to r2 by f2. And we also know power is nothing but intensity into area. I1 A1. So power incident is equal to power refracted out. Initial power is equal to final power. So this will be I1. This is nothing but area is pi r1 square. I2 pi r2 square. Therefore, I2 will be I1 r1 by r2, but r1 by r2 is f1 by f2. f1 square by f2 square. There. That's your intensity in terms of focal length. Right, Purada. Right, Ahana. Right, Niharika. Got it. So by adjusting the focal length, I can make the beam more intense or less intense. I can make it more diverged or more converged. Clear with this? It's a decent question. Any doubts on this? Clear, na? Pratik, Kush, Arush, Om, Vivan. Next thing. Turn in the page. Any doubts so far? This thing came in 2006 JEE, the year I wrote the exam. So we got a lens, focal length f. When you send a parallel beam of light, they meet at the focus. Great. Then what you did, you tilted the lens by a small angle theta. The lens got tilted by small angle theta, and you still kept the same light rays, nothing changed. Now the image will not form at the same place, image will move somewhere. Find the distance between the initial and the final image. Lens is tilted by small theta. Find the distance between images before and after tilting. So when you're tilting it, what is the catch actually? What does the lens think? Ask yourself. Let's say if the object is here, when you tilted this, you also tilted the principal axis, isn't it? And the object is here. So this lens will think now the object is at a certain height, isn't it? That's what it will think. So whenever you tilt the lens, it will think the object is at a certain height above the principal axis. That's what it will feel. Think. I'll give you a minute. How do we approach this? This problem, I did half of it, and then I didn't understand how to get the final answer. The options were not matching. I realized later on. See, first of all, look at this thing. So we are clear. This is the first image, isn't it? Now my question is this: the light ray which is going through the optical center, what will happen? That will go undeviated, isn't it? That will go undeviated. That means when these light rays hit here and meet somewhere here, that means the image will still lie on the old principal axis. The principal axis has shifted. This will be your new principal axis. And ray through the optical center is undeviated. So whatever image will form, that should still be on that line somewhere. We don't know where. It should be on that line. And second thing, we also know if the light rays are coming parallelly, they should be somewhere on the focus and perpendicular to the old principal axis, isn't it? This will be the new focus. Because the lens will think the object is now simply above the principal axis, isn't it? So it will try to find an image which is elevated above the principal axis. Now, since the rays are parallel, the image should form at the focus. But since it is tilted, the lens will think the image is at a height above the principal axis at infinity. So the image also will be slightly above or below the principal axis. Since rays are parallel, image should lie on a line perpendicular to principal axis and passing through the focus. Is that logic making sense, Adrian? Whenever you tilt the lens, think of like this. Instead of tilting the lens, you're just tilting the object, isn't it? So this length will be f. This angle will be theta. This will be the new image. This length will be f by cos theta. And previously it was f. So the image actually, most people will think the image also will tilt. Interestingly here, what happens, image won't tilt, image will simply get pushed forward. It will be on the same, it will be still on the old principal axis. So this line here is your old principal axis. The image will still lie on the old principal axis. So what you're asking for is distance. So the distance between them will be f sec theta, that is f by cos theta, minus f. I got till here. Then I didn't understand what to do. This is f sec theta minus f. This can be written as f into 1 plus tan square theta whole power of minus f. Since z theta is small, tan theta is approximately theta. This will be f plus 1 plus theta square half minus f. And I can also use binomial approximation since theta is small. F plus theta square by 2 minus f. The answer is f theta square by 2. Options were given like this: f theta by 2, f theta by 4, f theta square by 2, f theta square by 4. 1 plus x whole power n is approximately 1 plus nx. Is this clear, everyone? This is an old advanced PYQ. Any doubts on this? So that is a catch there. So if you keep this lens here, if you keep the object here, you will get the image here. Now, if you tilt the lens here, so the object will be here. So this will look like this. So that image, whatever is there, that will be somewhere here. You're getting it? That's how it looks. The image also will get shifted upward. That is one. Next thing, now there is an experiment. We have few more models, but let's do, there is one experiment here that is important in ray optics. Like I keep saying, the terminology is important. Most people, they goof up the questions not because it is tough or something, they don't even remember the words. So this experiment name is lens displacement method. It is also there for HSC ka 4-mark derivation. So what is this experiment for? This is an experiment to find the focal length of a lens. Simple experiment, but you should know the setup and everything. Let's say someone gave you a lens, you don't know the refractive index, you don't know the radius of curvatures, but you want to find the focal length. So what you need in this setup, first of all, you need a screen, you need an object, both are fixed. Get a fixed screen, get a fixed object, and get that unknown lens in the middle. This lens is a movable lens, you can move it left and right. Capital D is the distance between the screen and the object. Now what you do in this, consider a fixed screen and an object. As shown. Now keep on moving the lens, adjust the lens till you get a sharp image on the screen. Do you remember the video I showed you when you kept a candle, you got an image on the screen? So if you put it some random places, you'll get a blur image. So adjust the lens till we get image. So normally here now you have a bench here, bench with a scale ka markings. So when you keep moving the lens, you can measure at which point you got an image. When you do this, you will notice this will happen for 2 positions. So there are 2 positions where you get a sharp image. And then let's see how it works. So let's say position 1. You kept the lens here. Letters have gone here, the method here. Let this image be I1. Let this distance be X. Let this distance be Y. Position 2, object is here, screen is here. The reason why you get 2 images is because X and Y will get interchanged. This is Y and this is X. Check out the formula. If you try to apply the formula, you will get 1 by Y minus of minus X is 1 by F. Here, if you apply the formula, you'll get 1 by X minus of 1 by minus Y is equal to 1. You get the same thing. So object and image got interchanged, isn't it? If you keep the object in the place of the image, you will get the image in the place of the object. So there are 2 positions you will get this thing. And here to here, so you move this lens from here to here, let this distance be small d. There. So in this whole experiment, you know only 2 things. You know capital D, which is the distance between the screen and the object. This is in your control. This though you can measure. And you know small d, the distance moved by the lens. This also you can measure. You can measure the initial position, final position, and subtract them. That's it. Using only these 2 things, I need to find the focal length. So first equation, if I use the lens maker equation, 1 by y minus of 1 by minus x is equal to 1 by f. So we get the focal length is xy by x plus y. So somehow if you can get x and y values, my job is done. The second equation is x plus y is equal to capital D. That's the distance between the screen and the object. And next thing, look at here, x here and D here, isn't that will be y? The initial distance was x. When you moved the lens little forward, x plus d became y now. That is your next equation. So x plus d became y. So this is y minus x is equal to small d. Solve these 2 equations, you'll get y is equal to d plus small d by 2. X is equal to d minus d by 2. You're done. Take that and substitute here. We will get focal length is equal to d square minus small d square by 4d. This is your focal length, everyone. You got the focal length without any mu, r, nothing, with capital D and small d. So exam, there's a question like this. In a lens displacement method, distance between the object and the screen is 80 centimeters. When the lens is moved by 20 centimeters, we got a sharp image again. Find the focal length. That's it. People didn't have a clue what the hell was happening. When they heard the word lens displacement method, they were like, okay, we heard this somewhere. People had no clue what to do. People who know the result, it was straightforward. Clear with this? Check out the experiment. So the experiment simply works because that x and y get interchanged. You still get a sharp image here. Let's call this I2. Any doubts on this? Now, if you take this focal length, f is equal to d square minus d square by 4d. So there are a few precautions here. This experiment will fail if you 4df is equal to d square. This should be greater than or equal to 0. So we get d minus 4f must be greater than or equal to 0. So the capital D must be always greater than or equal to 4f. That means the distance between the screen and the object, if you keep it less than 4f, you will not get an image. You won't get an image on the screen only. So this experiment will fail. This is one of the precautions you have to take in this experiment. What is the distance between the object and the minimum distance? 4f. If you get only one image, that means you kept it at 2f. So this also gives you a result. The minimum distance between real object and real image is 4f. There you can ask a lot of questions here. Then you'll also notice something here. Let's say we keep an object here. Let's say height of the object is h. Let this be x. Let this be y. This is another nice question they asked. This is y and this is x. So when you kept the object in position 1, you will get an image here, which is h1. When you kept the object here in this position, you will get h2. You get two images of different heights. So in the first case, the magnification is v by u, which is y by minus x, which is height of the image h1 by h. In the second case, the magnification m2 is x by minus y, which is h2 by h. If you do the product of the magnifications m1 and m2 is equal to 1. And if you multiply these two, you'll end up with h1 into h2 by h into h is equal to 1. We get height of the object square will be root over height of h1 and h2. Quite a useful result. Straightforward question in the exam. So in the exam, the question was this. In lens displacement method, height of the images was, this was a p by q in means, 6 centimeters, 4 centimeters, and 9 centimeters. Find the height of the object. Itna hi tha question. If you don't know that formula, you'll not even understand what to do also. The height of the object will be root over 9 into 4. 6 centimeters, and you're done. Clear with this? That is the complete experiment. They can ask you 5 questions. Find the focal length, find the minimum distance between the screen for it to work, and find the minimum distance between object and image, product of magnification, and height of the object. Clear with this? This experiment is quite important. Any doubts on the experiment? Last thing, this we did before, Newton's formula. So instead of measuring the distances from the pole, if you try to measure the distances from the focus, then we have the formula x into y is equal to f square, same formula. The only problem here is we have two focuses, so how do we measure? So object ka distance is measured from f1, image ka distance is measured from f2. So how do you decide who is f1 and who is f2? The focus, which is on the side of incident light rays, is f1. So f1 is the focus on the side of incident rays. If the light rays are coming from the right side, then this will be f1. Y is the distance of image from f2. F2 is automatically the side of the refracted rays. What if you take a biconcave lens? Then how will you measure the directions? Because in this, if you look at the object and the image, both will be here only. This will be the object. This will be the image. Let's say somewhere here for simplicity. So the O ka distance is measured from here, X, and the I ka distance is measured from here, Y. Got it? You should measure it from the other focus. That's it. Newton's lens formula. There's nothing much there, but do remember they have been instances where they ask the question directly. The distance from the focus is 4 and 5 centimeters. Find focal length. If you know, you'll get it easily, or else you have to derive the whole thing. Clear with this? Yeah, that's a bit about lenses. So next class when we catch up, we'll do a few more problems on lenses. We have a little more varieties, and then we'll do something called combination of lenses and combination of lens and mirrors. That's quite an important thing. Yeah, mostly next class maximum we'll finish it off, and then I think next Friday, first half of the class, we'll wrap up the chapter, and then we'll start off with magnetism. Now, in case you have already solved this in your booklet and all, in the group I have sent you a sheet recently yesterday. That's an advanced sheet. It has around some 70 questions, covers all models. If you've already done your basic material, you just want something for revision, I think you can just do that sheet. That is taken care of. But if you have not done ray optics before, I would suggest you do your classes ka material or HCV or whatever booklet you're doing thoroughly end to end. Quite an important chapter. Okay, with that we'll wrap up for that day. So this week ka test is there are a lot of topics. I already posted in the